Okay, everybody, here we go on geometric sequences. There are a lot of different kinds of sequences. There are logarithmic and exponential, but we're only learning two in this section of our chapter. So geometric sequence is the second one. And instead of something added every time, it's something that's multiplied every time. And that thing that is multiplied every time is called the common ratio. The first example here says 3, 9, 27, 81. And that sequence has a common ratio of 3 because each number is multiplied by 3 to get the next number. The second example there says 4, 2, 1, 1/2, 1/4. In that case, the numbers are going down. We have a common ratio that's 1/2. So when the common ratio is less than 1, or between 0 and 1, that makes the numbers go down. The formula for writing one of these looks like a sub n, that's a subscript n, a sub 1 times r to the n minus 1. Again, your textbook does not include the subscript, but just for clarity, I've put a sub 1 to indicate that it's the first term of the sequence. For the two examples above, we could write them as a formula instead of a list. So for this first one, 3, 9, 27, 81, we could write 3, which is the first term, times 3, which is the common ratio, to the n minus 1. For the second one, it would be 4, the first term, times 2, the common ratio, to the 1/2. Oops, 4 times, the common ratio 1/2, and then to the n minus 1. The n minus 1 just stays in the formula every time. So first term, common ratio to the n minus 1. We should also be able to go backwards. So if we are given a formula like the one here, we should be able to find the sequence. We can do that either by plugging in 1 and then 2 and then 3 and so on. So for this one, if we plug in 1, we would have 1 times 2 to the 0, which is 1. If we plug in 2, we would have 1 times 2 to the first, which gives us the 2. If we just recognize the pieces, it can also be done faster. So 1 is our first term and 2 is our common ratio. So 1 times 2 times 2 times 2 and so on. We know that the fifth term is 16 because we've listed them out all the way to the fifth term. But if we wanted to skip straight to it without listing them out, we can also plug into that same formula. So that same formula can generate the list, or it can let us skip to a term. So if we wanted to find the fifth term without finding the ones in between, we would just plug in a 5. So a sub 5 now, instead of a sub n, is equal to 1, the first term, times 2, the common ratio. This 4 comes from 5 minus 1, which is just part of the formula. So 1 times 2 to the fourth is 16. That skips us straight up to the fifth term. The next thing we should be able to do is find the sum of the first however many terms. Now this formula is a little more complicated than the others we've been doing up until now, but it's still just plugging in. So if we want the sum of the first 10 terms of the sequence listed here, 2, 10, 50, 250, and so on, that's going to be a big number as they're getting big very fast. We can find it by plugging right in here. So the a sub 1 again is the first term. 1 minus the common ratio to the nth power. What is n? Well, in this example, it's 10 because it's the first 10 terms that we want. On the bottom, it's 1 minus 10 without the exponent. So here's where I filled in. My first term was 2 in the sequence that we were given. That 2 is multiplied by 1 minus the common ratio to the 10th, 1 minus 5. So it's the same thing on the top and the bottom, but one has the exponent and one does not. That exponent, again, comes from how many terms you're summing. When I plug into a calculator after that, it just gives me a number. So that's the sum of the first 10 terms of this sequence. Here's the part that is kind of a little magical to me. So if our common ratio has an absolute value less than 1, I know that looks like a 4, but I promise it says absolute value of r is less than 1. This is a big if. If the common ratio is less than 1, that means basically that it's between -1 and 1. It has a fraction as a common ratio. Then you can sum up the infinite list of all the terms, which is really kind of amazing. So This formula, which is actually even simpler than the one for the sum of the first n terms, this formula gives us the sum of every term in the sequence all the way up to infinity. If, for example, we go back to this sequence we used earlier, 4, 2, 1, 1/2, 1/4, and so on, it keeps going forever, but we can actually add up all the terms. Because the common ratio is 1/2, which is between -1 and 1. It has an absolute value less than 1. So we can find the sum of everything from the first term all the way to infinity. I've written it here as a formula, which is not necessary to doing the work. So we're just reminding ourselves what the formula looks like. First term is 4, common ratio is 1/2. And we're using a k this time, but to the k minus 1. But I go to this formula, it says a sub 1, that's the first term, 4 over 1 minus the common ratio. Notice that's the same denominator that we used here. And notice that we still have the a sub 1. We're really just eliminating that numerator. So I have 4 over 1 minus the common ratio, and that gives me 8, which is kind of cool. If we added up every number in this unending series, we would get 8. You can see that what we have so far is 4 plus 2 plus 1 plus 1/2 plus 1/4. That comes out to 6, 7, and 3/4. So we're already almost to 8, but because each fraction keeps getting smaller and smaller and smaller, we add less and less each time, and it would eventually add up to 8, which is kind of a magic trick to be able to add up a list of infinite numbers. Okay, I had to try several times to record this, so I've been through it several times, and I probably went through it a little quickly this time. Again, if you have any questions, please email or try to call me and we can video chat, or you can send me a comment in the discussion section of our Google Classroom. Good luck!